Hello, in this video we are going over the fundamental sets of solutions. How will we know if we get a solution to our differential equation? We will go over linear independent and dependent, the Wronskian and its properties, which will help us solve homogeneous and non-homogeneous uh, second higher order differential equations. Finally, we will go over Abel's theorem, which is an alternative method of computing Wronskian. So yeah, let's talk about Wronskian. Let's talk about the fundamental sets of solutions. Differential operator is the act of differentiating a function y(t) with respect to its independent variable. dy dt can also be denoted as big D and then lower subscript y, right? The symbol D is called a differential operator. For example, you can rewrite d cubed y over dt cubed equals d parentheses d parentheses d subscript y parentheses 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 equal is the same thing as uppercase D to the power 3 of y. So this right here is the same thing as this, which means the third derivative, right? Uh, differential operator can be combined into polynomial expression. So yeah, this is a polynomial expression. I'll just leave it as it is. And let's talk about principle of superposition. So L equals P of t times y double prime plus q of t of y prime plus rt of y. You've seen this before. And we know that y of t naught is equal to y of naught, and y prime of t naught is the same thing as y naught prime. So this will all make sense when we start doing the Wronskian. If we have found two solutions to the ordinary differential equation y1t and y subscript 2 of t, then y of t equals c of 1, y1t plus c2 y subscript 2 of t will also be a solution. Any solution, any solution to the differential can be written in this form. So by the power of superposition, we know that y equals c1 y1 plus c2 y2 and y of t naught equals y0 and y prime of t naught equals y naught prime, then y naught equals y of t naught, which is equal to c1 y1 t naught plus c2 y2 t naught, and then y naught prime is equal to c1. Basically, you took the product rule of this, right? Okay. Uh, so then we'll have to use when we're doing Wronskian, we're going to need to do Cramer's rule. If you forgot how to do Cramer's rule, go ahead and uh, watch it in the algebra section. A 2 by 2 Cramer's rule is pretty easy. It's a 3 by 3 that's a bit more work. So by using Cramer's rule, we can develop a condition that will allow us to determine when we can solve for these constants. Okay, so let's say here's the Wronskian. You have y of w of y1 comma y2 times t naught, and you set it up as a matrix, a 2 by 2 matrix. If you have a 2 by 2, you could have a 3 by 3. So basically, it's your y naught value, and then on this one here, this is the y prime, and then you have your y2 value, and then over here, it's your y2 prime. So basically, you got to take your y prime and your y2 prime, find that out, and then because this is a 2 by 2, you basically find the determinant. So you multiply these two out, right? And then subtract it by the product of these two. It should not equal to 0. So theorem, two solutions of y1 and y2. Val equals y prime of pt of y prime plus qt of y equals 0 are called fundamental solutions whenever it does not equal to 0. So when you take the Wronskian, right, you use Cramer's rule, and if it does not equal to 0, then that's how you know uh, you have a solution. You have a general form. Okay, yeah. So if it does uh, theorem, if it does equal to 0, then it's called a fundamental solution of whenever. Right. So if you take the determinant of the Wronskian, and if it doesn't equal to 0, then every solution is of the form y equals c1, y1 plus c2, y2. In fact, the Wronskian, the determinant of the Wronskian, if it does not equal to 0, then y1 and y2 are what's called linear independent. So if this, once you do the Cramer's rule and it does not equal to 0, then you know that y1 and y2 are linear independent. And if y1 and y2 are linearly dependent, then the determinant of the Wronskian, when it does equal to 0, then it's linear dependent. Okay, so if it does not equal to 0, it is linearly independent, and if it does equal to 0, then it's linearly dependent. That all sounds confusing, but let's do an example. So example 1 says compute the Wronskian and determine if the sets of functions are linearly independent. Okay, so what we have is y1 equals 2t squared and y2 equals t to the fourth. So this one's not too bad. So how do you find the Wronskian? The Wronskian is the determinant of y1 and then y1 prime, y2, and then y2 prime, right? So let's figure that out. So let's first find out what is y1 prime. That's pretty simple. What's the derivative of 2t squared? That's 4t to the 1, right? And then let's find y2 prime. What's the derivative of t to the fourth? That is 4t to the 3. Just simple power rule, right? So just put it in. So y1 is 2t squared. y1 prime is 4t. y2 is t to the fourth. y2 prime is 4t cubed. Okay, so this is a 2 by 2 matrix, right? How do we find the determinant? How do we find the determinant of a 2 by 2? Pretty simple. Uh, for example, if you go back to your algebra class, let's say you had a determinant of a 2 by 2, A, B, C, D. All you got to do is like multiply AD minus the multiplication of CB, right? That's it. It's pretty simple for a 2 by 2. 3 by 3 is a little bit, you might have to use Cramer's rule, right? Okay, so let's do that. So that would be, we multiply 2t squared times 4t cubed. So 2t squared times 4t cubed minus, and then it's the multiplication of 4t and t4, right? Okay. So put it all together. What is 2t squared times 4t cubed? That is 8t5 minus, what is 4t times t4, that is 4t5. Can we simplify these two values? Yes, because they're both to the power of 5. It's almost like saying 8x minus 4x, right? So that would be simplified as 4t to the 5th power. So this does not equal to 0, right? As long as t is greater than 0, you're fine. So yeah, so if t is greater than 0, then we are linearly independent, right? Okay, so yeah, this is our value. This is our answer 4t5, and it does not equal to 0. So we know it's also linearly independent. Okay, let's move on to example 2. That was not too bad. Example 2 says compute the Wronskian and determine if the sets of functions are linearly independent. So we have y1 equals 5x and y2 equals 5 raised to the x plus 1. So let's find our determinant. So let's first find y1 prime. What is the derivative of 5 raised to the x? Well, it's just going to be 5x ln 5, right? This is a constant raised to a power raised to the x. So if you forgot, go ahead and review your derivative rules. And what is the derivative of y2 prime? That is 5 raised to the x plus 1 times ln of 5. Okay, now we have everything we need. So put it in the 2 by 2 matrix. So it's going to be y1 here, y1 prime, y2 here, y2 prime there. So y1 is 5 to the x, y1 prime is 5x ln of 5, and then y2 is 5x plus 1 ln of 5, and then y prime is, whoops, got that mixed. So y2 is 5 raised to the x plus 1. y2 prime is 5 to the x plus 1 ln of 5. Okay. Now, how do we find the determinant of this 2 by 2 matrix? Just multiply this by this minus multiplication of this. So it is 5 raised to the x times 5 raised to the x plus 1 times ln of 5 minus, so then you multiply this out. So it's going to be 5 raised to the x plus 1 times 5x ln of 5. Okay, so what can you say? They're exactly the same thing, right? This times this is this. So it's almost like saying x minus x because they're identical. And what's x minus x? 0. So this is going to be 0. And we know that if it equals to 0, the determinant of the Wronskian, if it equals to 0, it's linearly dependent. Okay. Okay, let's move on to example 3. Okay, example 3 says, compute the Wronskian and determine if the sets of the functions are linearly independent. So we have y1 equals t to the negative 1, and then y2 is t raised to 3 halves. Okay, so first up, I'm going to find my y1 prime. What's the derivative of t to the negative 1? It is power rule, so that's negative t to the negative 2. What is the derivative of y2 prime? Same idea, power rule. It would be 3 halves t to the 1 half. Okay, all I did was I applied my power rule. So set up your determinant for your Wronskian. Okay, so on the vertical column, it's y1, which is t to the negative 1. And then it's y1 prime, which is negative 2 squared. And then y2 is t to the 3 halves. Y2 prime is 3 halves t to the 1 half, right? Let's find the determinant of that. So basically, uh, it's this times this, which is t to the negative 1 half times 3 halves t to the 1 half minus this times this. That's it. And when you put it all together, this times this, that is going to be 3 halves times this one is 3 halves. And then negative, remember when you're multiplying with the same base, you add. So what's negative 1 half plus 1 half? And negative 1 half. And over here, it's going to be a minus t. And then 3 halves plus negative 2 is negative 1 half. Okay, two negatives becomes a positive. And what else can you say? This is a power of negative 1 half. This is a power of negative 1 half. They're the same base. I mean, same power, so you can combine this with this. So basically, you add the coefficient, right? What's 3 half plus 1? It is 5 halves. And then power t to the they're both, since they're the same, you leave it as negative 1 half. So this is not equal to 0. So this proves that this is linearly independent. Okay. Let's move on to example 4. Okay. Example 4 says compute the Wronskian and determine if the sets of functions are linearly independent. Now we have some trig stuff. So we have y1 equals 9 cosine of 2x, and then y2 is 2 cosine square x minus 2 sine square of x. What could we do? Let's find our y1 prime. This is not too bad. It's just 9 is a constant, so basically you take the derivative of cosine 2x by applying chain rule. So we know that the derivative of cosine is negative sine. And then you take the derivative of 2x, which is 2. And then so it's 2 times negative 9, because this the derivative of cosine is negative. So negative 9 times positive 2 is negative 18. So it's going to be negative 18 sin of 2x. And what about this one? Yikes. What could we do? Well, it looks like I could take out a 2. So if I took out a 2, this would be 2 cosine square of x minus sine square of x, right? And then what could I do here? Do you see an identity of cosine square x minus sine square x? Yes, it's a double identity, right? Uh, one of your a double identity, we know that cosine square x minus sine square x is also the same thing as cosine 2x. So this is really 2 cosine of 2x. Okay. Now, how do you take the derivative of this? Simple, right? It's just you take the derivative of cosine. It's chain rule, right? You take the derivative of cosine, which is negative sine. So it's negative sine of 2x, and then you apply the chain rule to the root of 2x, it's 2. And then you still have this positive 2, and then you have this extra minus, so that is negative 4. Okay, so we have our y1 prime and our y2 prime, so that's all we really need. So it's going to be, the Wronskian is going to be set up like this. We have 9 cosine of 2x, and then the derivative of that is negative 18 sine of 2x, and then y2 is, you can rewrite it as just 2 cosine 2x. I think that's going to be easier. 2 cosine of 2x, and then the derivative of that is negative 4 sin of 2x, right? Okay, now we just find the determinant, so you just multiply, right? So it's going to be this times this. So that would be, just write it out if you get lost. 9 cosine 2x times negative 4 sin of 2x minus, and then it's this times this. Okay. Put it all together, you get negative 36 cosine of 2x sine of 2x. And then over here, two negatives, and the negative becomes a positive. So that's plus 36 cosine of 2x sine of 2x. Okay. These are practically identical, right? So you just basically add the 36 and negative 36, which is 0. And what do we know about 0? It is linearly dependent. Okay. Okay, let's do another example now. This one is going to be a 3 by 3 matrix. This one. Okay, example 5 says compute the Wronskian and determine if the sets of the functions are linearly independent. Okay, so we have y prime or y triple prime minus 6y prime double prime plus 11y prime minus 6y equals 0. Okay, so this time we have a y1, a y2, and a y3. So my y1 is e to the x. Yes, our y1 is e to the x. My y2 is, what's the derivative of e to the x? It is e to the 2x. And then my y3 is e to the 3x. Okay, so how are we going to set it up? We're going to set it up like this. So here is going to be y1, y2. This is y1 prime, y2 prime, y3 prime, and then this is y1 double prime, y2 double prime, and y3 double prime. So that is going to be our y1 is e to the x. My y1 prime, what's the derivative of e to the x? E to the x. And then what's my, take the derivative of e to the x again, that's also e to the x. My y2 is e to the 2x, right? E to the 2x. What is the derivative of e to the 2x? It is 2e to the 2x. And what is the derivative of 2e to the 2x? It's just the same thing, but take the derivative of 2x, which is 2, and then times it by this extra 2. So that's 4e to the 2x. Okay. And what is my y3? My y3 is e to the 3x. What is the derivative of e to the 3x? It is 3e to the 3x. And then what's the derivative of 3e to the 3x? 9e to the 3x. Okay, so how do we take the determinant of this? This is now a 3 by 3. It's not a 2 by 2. Um, so you kind of have to remember Cramer's rule. So if you recall Cramer's rule, let's say a Cramer's rule was like this. So let's use letters. You have an A, B, C, D, E, F, G, H, I, right? And if you recall, this sign is positive minus positive. It just changes values. This is negative plus negative. Okay, so in Cramer's rule, what you want to do is get rid of a row and a column, and then that would give you like a 2 by 2 matrix, which is easy. So, for example, if you got rid of this uh, this row and then this column, so if you get rid of A, you have to get rid of that entire row and then this entire column. And then now you're left with these two matrix. And then you're going to multiply whatever this value is, uh, you're going to multiply that and then you follow the signs. Okay, so let me show you. So if we got rid of this e to the x, like if you got rid of this row and then this column, right? So it would be plus, because e to the x is plus, right? It's going to be e to the x times by the matrix. So if you got rid of that, you're just left with 2e to the 2x, 3e to the 3x, 4e to the 2x, and 9e to the 3x, right? So you're going to left with 2e to the 2x, 3e to the 3x, 4e to the 2x, 9e to the 3x, right? Minus, because remember the sign changes from positive, it always just naturally changes from positive to negative. And then it's going to be, now if you got rid of this, try this e to the 2x. So I'm going to use this number, this coefficient, and then you're going to have to get rid of everything get rid of this entire row, and then this entire column with the e to the 2x. So now you're left with e to the x, e to the x, 3e to the 3x, and 9e to the x, right? Okay, so let's do that. So it's minus, and then it's going to be e to the 2x, and then your leftover is e to the x, e to the x, 3e to the 3x, 9e to the 3x. Okay, and then if I got rid of this number, it's going to be plus e to the 3x, right? The sign now becomes positive because we was a negative, now it becomes a positive. And then if you got rid of this one, you're left with e to the x, 2e to the 2x, e to the x, 4e to the 2x. Okay, Now, what we'll do next is we can take the the determinant of a 2 by 2 matrix, right? So let's take this. You just multiply this, subtract it by this multiplication, and then FOIL out the e to the x, right? So that is going to be e to the x times 2e to the 2x times 9e to the 3x minus, and then do this, you know how to, it's, we could do this determinant, right? So it's minus e to the 2x, and then just multiply 9e to the 3x. So it's 9e to the 3x times e to the x minus e to the x times 3e to the 3x. And then it's going to be plus, I'm going to put it here, e to the 3x times, so multiply this out, e to the x times 4e to the 2x minus e to the x times 2e to the 2x. Okay. Okay, so now we have to carefully do the algebra. So this would be 9 times 2, which is 18, e to the 5x minus, so this, so, okay, so be careful. It's this times this minus this times this. So that would be 18e to the 5x minus 12e to the 5x minus e to the 2x. It would be 9e to the 4x minus 3e to the 4x plus e to the 3x times 4e to the 3x minus 2e to the 3x. And when simplified, it's going to be e to the x times 6e to the 5x minus e to the 2x times 6e to the 4x plus e to the 3x times 2e to the 3x. And when you simplify that, that's going to give you 6e to the 6x minus 6e to the 6x plus 2e to the 6x. And what can you, well, we know that this cancels. So now you're left with 2e to the 6x. And we know that does not equal to 0. So this proves proves that they are linearly independent. Okay, so that was a long one because it was a 3 by 3 matrix, and we had to learn about or review Cramer's rule. Okay, so what if I told you there's an easier way? Um, if you don't want to do the Wronskian, you can actually, let's talk about Abel's theorem. Basically, it's just an alternate method of computing Wronskian. So if y1t and y2t are the two solutions of y double prime plus pt y prime plus qt y equals 0, then you can use this formula. w equals ce raised to the integral of negative pt dt. Okay, let me show you an example. So example 6, without solving, determine the Wronskian of the two solutions to the following ordinary differential equation. So we have I think I'm in the wrong. I think I'm on the wrong. Oh, here we are. Okay, so what is our P of t? So my P of t is basically this number, negative 2 over t. So what is the integral of that? So we have to put it in the form of w equals c e integral of negative 2 over t dt. So what is the integral of negative 2 over t dt? Well, you can take out this minus 2, so that's minus 2 of 1 over t dt. And then the integration of 1 over t dt is ln of absolute value t. So you took out a minus 2, and then also you have an extra minus. So that is going to be w equals c e 2 ln of absolute value of t. And then what can you do with this 2? Put that in front of the t, so that's going to be w equals c e ln of t squared. Okay? So what happens is the e and the ln cancels. So now you're left with c t squared, and it does not equal, or t does not equal to 0. So yeah, this is your answer. Okay, let's do another one using Abel's theorem. Let's do one last one. Okay, example 7 says, without solving, determine the Wronskian of the two solutions to the following ordinary differential equation. We have parentheses 1 minus x squared times y double prime minus 2x y prime plus alpha times alpha plus 1 equals to 0. So we have to first put it in the correct form. So we have to get rid of this 1 minus x squared first. So how I'm going to do that is divide everything by 1 minus x squared. And we get, so now we get it in the form of y double prime plus p t of y prime plus q t of y equals 0. And now we have it. Oh, so this is what we have to put it in. Now we have y double prime over here with minus, it's going to be minus 2x y prime over 1 minus x squared plus over here, nothing cancels, so you're just left with alpha times alpha plus 1 over 1 minus x squared equals to 0. The next step I would do is find out my P of t. My P of t is this whole thing. So my P of t is negative 2x over 1 minus x squared. Okay, step 2. We have w equals c e, the integral of negative, and then you have negative 2x over 1 minus x squared dx. So let's take the integral of this. What's the integral of 2x over 1 minus x squared dx? So my u is going to be 1 minus x squared. My du is going to be, the derivative of 1 is 0, the derivative of negative x squared is negative 2x dx. And what should I do? We should get rid of this negative because we only have a positive 2x dx, right? So I'm going to multiply everything by negative. So I get negative du equals to positive 2x dx. Okay, so it's going to be w equals c e, the integration. So it's going to be 1 over u minus du, right? And that's going to be c e. And what's the integration of 1 over u? It's ln. And then you have a minus, so it's going to be minus ln of u, and I'm just going to replace my u with 1 minus x squared. And what do I do next is this minus goes in front, so it's going to be c e ln of 1 minus x squared to the negative 1. And what happens is the e and the ln cancels, so your final solution is good. Your final answer is going to be y equals, I mean, not y, w equals c over 1 minus x squared. Let's just put it as a positive, so it's going to be absolute value of 1 minus x squared. And yes, I'm going to put the absolute value because we don't know what x is. So this is my final answer. Yeah. Okay. So yeah, that wraps it up for this lecture. I'll stop here.